two or more variables are not separated. So if you'll notice in the observational study we looked at, they were separating by a lot of different characteristics. But if you forget to separate one, then you have what's called confounding, or kind of muddling the results. So if you're measuring lung capacity and you forget to ask, maybe you're studying smoking and non-smoking and measuring different lung capacities, and you don't separate the runners from the non-runners, well, someone who runs all the time is going to have a greater lung capacity regardless of if they smoke or not. So those are some of the confounding variables, different things that can mix in to your results. So this is when the results from the study could be due to factors other than what you were trying to measure. And we cannot show any causation. We can only show association with an observational study. We can't say smoking causes a lower lung capacity. All we can say is that they're related, or maybe they're not related. So we cannot come to the strong conclusions with observational studies. So a little bit more about confounding. Confounding has what's called a lurking variable. Sometimes there's one, sometimes there's more than one. So a lurking variable is again an explanatory variable that was not considered in the study, but that's affecting the value of your results. And so some lurking variables in our observational study that we looked at before, I think I put it again in your notes. This is the same scenario as before, and I want you to look for all the lurking variables they were thinking of. So they did matching based on age. That might be something they were trying to consider. Gender, region of residence, different locations. And then they also looked at demographic background, medical history, and smoking status. All of these things that they were separating out were potential lurking variables. They were trying to divide them out so that they would not get mixed into their results. So they really did a good job of separating as many of the lurking variables that they could think of. So usually in an observational study, there's at least one lurking variable, and there's all kinds of different examples of different things that can get in the way and muddle up your results. On to designed experiments. There are pros and cons to designed experiments. So some of the pros is that you get those more reliable results. You can show that one thing caused another to happen. The biggest thing you have to look at, though, is control. You have to control for some of those confounding variables. You have to control it as much as possible, the environment, the different variables, as much as you can control for all of those things. And so in a well-designed, well-controlled experiment, we can show causation, which is why experiments are so powerful. Some of the cons, however, is it's much more expensive, both time and money and resources and anything else you can think of. It's going to be more expensive. It takes more time to plan it, design it, implement it, and then analyze it. It's a very long process. You cannot get quick results. And sometimes it's not possible, or it could be harmful to run experiments. So if I wanted to run an experiment on smoking, I can't make a group of people smoke that are not current smokers. If I was studying tattoos, I wouldn't make people get a whole bunch of tattoos. If I was studying hair loss, I couldn't make someone lose their hair. So there's some situations that you just cannot run an experiment. You have to do an observational study. So design experiments are great if you have the time and the money and the resources, and you're not going to hurt anybody in the process. All right, and then the book talks about different types of observational studies. Again, this is not something I'll be testing over. There might be a question on your homework about the 3 different types of studies. It's on page 18 of your textbook, but it's not something we'll be testing over. All right, the last part of this section kind of introduces the next section, and that's on census data. So a census is a list of all individuals in a population along with certain characteristics of those individuals. So every few years, I think it's every 10 years, our government sends out a census, and they want every single person to answer every single question of this census, and they want everybody to mail them back in a timely manner. So the big question is, how reliable is the census? It seems like it would be perfect if you can get every result from every person. Then you would have a perfect set of data. So the next slide, I want to show you an example of what it means to take a census. So what I'd like you to do, don't really read all of this. This is a silly story about a frog. You can read it if you'd like to. It's just kind of a silly story about a frog. I'd like you to take 2 to 3 minutes. I want you to pause the video, and I want you to count the number of G's that you can find, lowercase or uppercase, the letter G, so a lowercase g or an uppercase G. Just count throughout the whole story, count how many G's you found in the story. I want you to count every single G and then write your results in the bottom corner. Count how many G's and write your results. Go ahead and pause the video. Only give yourself 2 to 3 minutes. You can time yourself and count the number of G's. I'm going to let you pause the video. Alright, so if you've counted all the G's and you have your number in the corner, hopefully you got it right. Hopefully it wasn't too hard to count those G's. Unfortunately, when I do this little experiment in a classroom, we all have different answers here. Almost everybody has a different number there. And everybody's pretty surprised that the numbers are all different, because really they should all be the same. And if you're curious, the exact correct answer is 83. And in my semesters of doing this, I've never had a student get 83. So that is the correct answer if you want to count them again on your own time. But this is just to show that a census, trying to calculate every single value of whatever, is almost impossible and highly inaccurate. So that's just a little experiment there. And that takes us to section 1.3, which is on simple random sampling. So sampling is used because a census just is impossible. You can almost never get the entire population data on anything. So we use sampling to help us. So simple random sampling is the most common. We call this an SRS. And you're going to need the random digit table, which is on your formula table card. If you go into My Math Lab, there's a tab that says Formulas and Tables. And there's a PDF file that you can print out. It's going to have all the formulas you need for the course, all the tables you need for the course, and we're going to be looking at Table 1, which is on page 5 of that file. So if you want to print that out, I have it on the next couple slides, but I would print out a set of the PDF file so that you have a hard copy to help you out. Alright, so how to take an SRS. The first thing you need to do is numerate, or number off, a list of the entire population. So give everybody a unique number. Each individual needs a unique number, and this is called a frame. So it's a list of everybody in your population. Then you're going to select N numbers from the random digit table. N is what we call our sample size. We'll be using that same letter, lowercase n, for the entire course. When you see lowercase n, we're referring to the sample size. There's 2 different ways to sample. You can sample without replacement, which is when you ignore any repeats, or sometimes, not very often, you sample with replacement where repeats are okay. This is like a raffle. If they draw the same number twice, they disregard it, or sometimes you just get to win both prizes. But we're going to be sampling without replacement most of the time. Alright, so here's my frame. This is everybody in my population. I think it's 30 different businesses that we're trying to sample. I think we're going to be sending out, I think those situations about sending out flyers, it's on page 24. So we have 30 people in our population. We've numbered them 1 to 30. Notice that the numbers 1 through 9 are actually 0, 1, 0, 2, 0, 3, all the way through 0, 9. Seems a little strange for us, but if we have 2 digits for the number 30, then every single one needs 2 digits, and you'll see why in just a minute. So we're sampling 2 digits at a time. So the next page I have a section of the random digit table, and you can print this off again in the PDF file. So if you have, I just kind of want to show you how this works. You have different rows down the side and columns across the top. Technically, all these numbers are squished together, but they put spaces every 5th digit just to kind of help you find things. So this is row 1. The next digit is row 2, then row 3. I'm sorry, not rows, columns. Column 1, column 2, column 3, column 4, column 5. So it says 1 to 5. Then we have column 6, 7, 8, 9, and finally column 10. So it's columns 6 through 10. So every digit down is a different column. 11, 12, 13, 14, and then 15, 16, 17, 18, 19, and then 20 down. Those are columns, and then rows. So the homework will have you start at a particular row number and a particular column number. For simplicity, we are all going to start on row 1, column 1 to help keep this easy. So row 1, column 1 is the digit 8. However, in our frame, we need to count 2 digits at a time. So we're going to use the number 89 as our first random number, 89. 89 is not going to help us because we only have the numbers 1 through 30. So we just ignore 89 because we don't need it. The next number is 61. Well, 61 is also not what we need, so we're going to ignore it. So we ignored 89, we ignored 61. Then we get to number 11. That means that number 11 is the first selection for my sample. So I think on the next page I have a space for you to write that down. So number 11, which is Fox Studios, is our first business we selected. Then we keep going down. 27 is our next in our sample, so there's 27. And then the next number down is 36, so that's not going to help. 81, ignore. 59, ignore. 46, ignore. We get to 24. So number 24 is in our sample. And you just keep going. 98, ignore. 14. There's one in our sample. So we have 4 so far in our sample. We need 1 more. So we keep going. 55, ignore. 96, ignore. 38, ignore. 85, ignore, ignore. And then we get down to 10. So number 10 is the last in my sample. So that's using the random digit table. You always go down. Sometimes you count single digits, double digits, triple digits. Sometimes you'll start at different columns or different rows, but you always go down. If you get down to the bottom, let's pretend like we kept going. Once you get down to the bottom of one of the columns, you go immediately next to it. Let me change colors. You go all the way up to the top immediately next to it for the next. So 39 would be the next in my sample. I know it's hard to see on mine, but hopefully you can see it on yours. And then 45, 45, and you keep going down. If you get down to the bottom and you need to go back up to the top, then 22 would be your next one. So it's next to the next column over at the top, and then again you just keep going down. So if you're having trouble with that, just let me know. So that is how to choose a sample of size 5 using the random digit table. Another way to do the same thing is to use the calculator. We don't really need to use the calculator, but I do want to show you that it is an option. In your homework, you'll be using the random digit table, but there is a way to do this in a TI-83 or a TI-84 calculator. Hopefully you can see mine okay. So it says to type any 2-digit number and press the store key. So I'm going to pick a 2-digit number, any number is fine. The store key is right above on, STO. And then we're going to go to math. The math button is below your alpha button, math. Go over to probability, PRB. Whoops. And down, option 1, random. So we're taking our random number and we're storing it in random. What this tells the calculator, it gives it a random starting place. It's kind of like if we were on the random digit table, if I just gave you a random starting place. We're doing that same idea in the calculator. From there, we're going to go to math again, over to probability again. This time we're going to go down to option 5, random integer. Random int is random integer. The first number you put in is your lowest number. The second number is your highest number, and then your sample size. So I want a number between 1 and 30. The comma button is above 7. We're going to be using that a lot. Comma is above 7. And then comma 5. So it's going to spit out 5 numbers between 1 and 30. 27, 29, 10, 5, and 7. So I can use those 5, and those would be a different sample using the calculator. Sometimes when you do this, you get a repeat. If you get a repeat, just hit enter again, and it'll spit out 5 new ones. So this time I got 13 twice. I'm going to hit enter again, and there's a nice set of 5. So if you're ignoring repeats, just keep hitting enter until you don't have any repeats. So again, I got 21 twice. If I hit enter again, there's a set without repeats. So it just randomly generates numbers between 1 and 30, and it spits out 5 at a time. So that's one way to get random numbers. I don't think we have to worry about that for this course, though. I think that always depends on the random digit table. All right. That concludes section 1.3. Section 1.4, there are different sampling methods other than an SRS. So an SRS, a simple random sample, is the most common, it's the easiest, if we can numerate the population. There's also a technique called a stratified random sample. There's a systematic sample, a cluster sample, a convenient sample, which is we'll talk about, and then what we call a multi-stage sampling. So I'm just going to briefly go over these different types of sampling other than a simple random sample. So a stratified random sample is when you separate the population into what are called strata, which the word we like to use is groups, based on a common characteristic. So I might sort something by size, I might sort some people by their career, might sort people by their age, their weight, their height. There's all kinds of different ways to sort people, smallest to biggest, or different career paths, or whatever it might be. Then you take a simple random sample from each stratum, which again just means group. So I might have a group of small, medium, and large, let's say rocks, and I'll take a simple random sample from the small rocks, a simple random sample from the medium rocks, and a simple random sample from the large rocks. So I'm getting a simple random sample out of each group. So this is effective when the population is easily categorized. For example, Lone Star likes to separate students by age, course credits, GPA. They sort by all kinds of different things, and then they take a random sample from each of those groups. So they always talk about different age groups. So they might do 18 to 24, 25 to 30, different groups, 31 to 35. So they'll separate them out into groups and then take a random sample from this group and a random sample from that group, etc. Sometimes, though, this is impossible. Sometimes you can't separate anything into groups. If you're surveying different cars entering the freeway, if you're surveying random or sampling random animals, wild animals, you can't really separate them into groups. So sometimes this is impossible, but it's very effective if things are easily categorized. The next type is called a systematic sample, and it's selecting, the book says every kth, which is kind of a weird notation, kth individual from the population to create a sample. So a manager might survey every 10th customer in the store. That would be K equals 10. So every 10th customer that walks in, the manager is going to survey them. They do this a lot at retail stores. The store manager kind of stands by the door and kind of counts as customers come in, and they'll survey every 5th or 10th or 20th customer in the door. Registers also do this. Cash registers will automatically print surveys on every 50th receipt. So Chick-fil-A does this. They'll randomly send a survey, print a survey on the receipts. Kroger does this. Lots of different retail stores do this, and it's just kind of the system has been programmed that every 50th printed receipt will get a survey on it. So it's called a systematic sample because it's a system. Every so often it prints the receipt or it asks for the survey. Then we have what's called a cluster sample. And this is randomly selecting a location or a time and surveying every individual in that location or time frame. So for example, this has happened here at Lone Star, the dean can randomly pick a classroom. So she'll kind of walk around and randomly pick a classroom, and then she'll sample every student in that classroom at that time. So she'll ask every student there the same question. Store manager might do something similar, survey every customer that comes into the store between the hours of 12 p.m. and 1 p.m. Every single person. That's called a cluster. So you pick a location or you pick a time and you cluster, you sample everybody in that location or time. Then we have what's called a convenience sample, which is what it says. It's based on convenience. So I know Carl's Jr. has what's called a self-selected survey. They just put the response cards on tables, and maybe you'll fill it out, maybe you won't. That's called self-selected. You decide if you fill out the survey or not. That's convenient for Carl's Jr. They can just leave them on the tables and they don't even have to worry about them. There's also voluntary responses. So Google reviews, any sort of online reviews is voluntary. You choose if you want to do that review. So self-selected, voluntary, kind of the same idea. Sometimes there's those pop-up surveys on websites. That's very convenient that they can just program that survey to pop up. Any type of convenient sampling, any of these, or maybe you just ask the first 5 people you see a different survey question, that's convenient for you. Anytime that happens, we get unreliable results. So this sampling is based on ease or convenience, and it is not scientific. It's not random, it is not programmed, it is not anything, it is just convenient. So convenient sampling is not the correct way to take a sample. And finally, we have multi-stage sampling. This is for very large scale surveys. So they might combine different types of sampling into one large scale survey. So they'll combine stratified with cluster with simple random all combined together. So there's an example on page 35 of a multi-stage sample. So there'll be some questions where you just have to identify the type of sampling being used. The next section is 1.5. It's pretty quick. Bias in sampling. Anytime you take a sample, there is potential bias, and usually you can always find something that would be considered bias. So there's some different mainstream kinds of bias. I don't want you to stress too much about the different kinds. Just know that generally when you take a sample or do a survey, there's some sort of bias going on. So there's one kind called sampling bias. This is when we have convenient sampling or under coverage, so not everyone has had a chance to be selected. So the sample itself is bias. Maybe you only asked people in a wealthy neighborhood, or you only asked younger people, or you only asked, it just depends. So you've under coverage, you have not represented the population, and you have sampling bias. And there's another type called non-response bias. That is what it sounds like. So when you have voluntary surveys, people just won't respond. I get those receipt surveys all the time. I don't always fill them out. So you might notice that they'll call you back, which doesn't happen as much. Most of the time it's an incentive. You can enter to win money, or you can get a free food, or free whatever, I'm going to say food, a free item, or sometimes you can get 10% off your next purchase. So they have all these different incentives to help you, encourage you to do the survey, even though it's completely voluntary. And so if we choose to not respond, that's what they call non-response bias. The third main type of bias is called response bias. This is when you have chosen to respond, but the survey was not conducted correctly. And that can open a lot of doors and a lot of cans of worms, because the survey itself was not done correctly. The responses given were from a biased question. So the book talks about some different kinds, and again, there's a lot. There's one about interviewer error. The interviewer influenced your answers. So if a police officer ever asks you if you speed, you might be influenced to answer a certain way. There's also misrepresented answers, inflated or deflated results. If you ask a woman her weight, that's one where we might deflate our response. And so you can kind of fudge your numbers a little bit and misrepresent your answers. There's also, this is a big one, the wording or order of the questions. So wording is a very big deal. There's also order. Salesmen, saleswomen, they worry about the order of their questions so that to get you to answer a certain way. So the phrasing might say, do you agree with killing innocent beings? And it influences your answer because of the way they worded the question or the order they asked the question. Then there's just the type of question, an open question or a closed question. If they make you answer yes or no to something that's not necessarily a yes or no type of question, then that can influence your results. There's also just human error. That happens. The data is not entered correctly, so then bias results. And there's a ton of others. Again, don't stress about all the different kinds. Just know that there's a lot of different ways bias can occur. So that one's quick. That's all section 1.5 is. And finally, with section 1.6. This is again the longest chapter. It's got a lot of material in it. All right. So we have experimental design. Experimental design could be its own course. There's a lot that goes into experimental design. This is again